Okay, so today we're going to be taking a look at doing the second derivative of parametric equations. Of course, understanding them as parametric functions. So if you take a look at the example, it says to find d squared y over dx squared. So we know that's a notation for a second derivative. Okay, and we're typically using that when it's the fact that we're taking the derivative of dy over dx with respect to x. Okay. So let me write that out. You are probably copying down the example, but there is something else that you need to write down as well. So perhaps leave some space if you're ready, start copying the example, or you can start writing that now. Okay, so what I was describing before, okay, is that this notation is brought about because we're taking the derivative with respect to x of dy over dx. Now, as you look at the notation, okay, of means to multiply. So if you look at this, you could see definitely why we have like a d squared y in the numerator. And for dx squared, it's just a common way that instead of writing this as like dx times dx or the dx being in parentheses squared, we just have that square there. It's just known and understood that we're squaring the dx, not just x. So, let's get to more of the notation and the understanding that I told you to leave a space for in your notes. So now, we already went over parametric equations. There are two equations. There is an x of t, a function of t or time. T is our parameter. And y of t. This gives us our parametric equations. And we can easily find x prime of t, or that could be written as dx over dt. And we can easily find y prime of t, which is dy over dt. Now, I accidentally wrote something incorrectly. So if you're copying this down, you should be like jotting something down. This is not what I need you to copy down, but this is, we want to say this is dx over dt. I said the right thing, I wrote the wrong thing, and let me make sure that looks like a y. Alright, so we know how to do this, and we should also know how to find dy over dx. It is done by taking dy over dt over dx over dt. And you guys know when you divide something like that, you could do keep, change, flip, but you could realize why the dt's are no longer there. This is a really good expression for dy over dt. So now if you take a look at the expression that we have here, up at the top, so we need to take the derivative with respect to x of dy over dx. Okay, so let's erase some work here, or I should say notation, so I have plenty of room. In the meantime, please make sure you get this down in your notes. Alright, so take a look at what d squared y over dx squared is. So it's the derivative, okay, with respect to x of dy over dx. Okay, so we know what dy over dx is for parametric equations. It's over here. And I just wrote the same thing twice. We can write this as, okay, the derivative of y with respect to x. I'm just writing y prime. Very simple notation. It doesn't actually tell me if it's with respect to x or respect to t. But I just want to go to like a simple notation so that you can understand what we need. And if you look at this now together, we need the derivative of y prime over the derivative of x. Now, the derivative of x is x of t, okay? So now, when you take the second derivative, d squared y over dx squared, we're going to need to divide by dx over dt. And what do we have in the numerator? We need to take the derivative, okay, of our dy over dx. That's what it says there. Okay, so we're taking the derivative of what we get when we do dy over dt over dx over dt. So essentially, let me erase the top so I can describe this to you. We need to find dy over dt, dx over dt, okay? Divide them in the order that I just described it. Take its derivative and then divide it by the derivative of x with respect to t. So essentially, okay, we need to just take the derivative of this answer. Okay, so we just need the derivative of dy over dx, but we need to make sure that we divide by dx over dt. Now, I did all of that to stress we need to divide by dx over dt because most students forget that part. And going through a notation and showing where it comes from, why it's necessary and needed, sometimes gives more of a foundation, more of a strength, more of maybe a memory, why I'm describing all of this to you. And that's why. Okay, so just remember, we take the derivative of dy over dx, but we divide it by dx over dt. Okay, so now we're ready, set to do the example. Okay, so hopefully you had some time to write it down. But if not, I'm going to read it to you. So as I'm reading it, you'll still have some time to jot it down. Okay, in the example, it says to find d squared y over dx squared as a function of t if x is equal to t minus t squared, y is equal to t minus t cubed. Determine the interval or intervals in which the curve is concave down. Okay, excellent. So we know that we have parametric equations here. Okay, because it's being defined as an x of t and a y of t. And in order to find d squared y over dx squared, we're going to find dx over dt. Okay, so we're taking the derivative with respect to t, so that's going to be 1 minus 2t. And we need to find dy over dt. Okay, so if we take the derivative y with respect to t, we get 1 minus 3t squared. So dy over dx is going to be the dy over dt, the last answer I just wrote, over the first answer I have, which is 1 minus 2t. Okay, so this is dy over dx. So we didn't get to d squared y over dx squared yet, but we are now. Okay, if you take a look at dy over dx, we have a fraction. So if we need to take its derivative, we're going to need to do the quotient rule. So let's start to use some space for some scrap work. So we're going to do bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. Okay, so it would probably be best if we simplify this the best we can. So if we take a look at our numerator, we have negative 6t plus 12t squared. And if I subtract this negative 2 over here, it's going to be positive 2. So that way I'm adding, which is always great. So if I distribute a positive 2, I'm adding 2, and I'm subtracting a 6t squared. So now if I combine that all together, this is going to give me 6t squared minus 6t plus 2 over the quantity of 1 minus 2t squared. So I want to leave it a little bit at the end, just in case you didn't get that down, so it's still at the bottom. While I read the next part, it says determine the interval or intervals in which the curve is concave down. Okay, so we know that in order to determine the concavity of a function, okay, that could be a curve, we would take a look at its second derivative and determine if it's positive, that means it's concave up. If it's equal to 0, that could mean a point of inflection, depending on if there's a sign change before and after that particular value that we're looking at on our curve. And concave down if it's negative. Okay, so up positive, down negative, inflection point equals 0. So what we need to do is take a look at what we have for d squared y over dx squared, okay? And we have 6t squared minus 6t plus 2 over the quantity of 1 minus 2t cubed. What we're going to do is set that equals 0 and find at what time, okay, because we're going to find t instead of an x. At what time t, maybe there is a place that the concavity would change. And if that's the case, then we are going to be able to see if there's an interval, or maybe all the intervals, there is a place where our curve is concave down. But we're going to describe it in terms of t. That is okay because we are working with parametric equations, and it is determined by a parameter t. On a side note, parametric equations can also be called a vector-valued function. A vector-valued function is a function in which there are one or more variables involved. So since you can see we have x, we have y, we have t, this is an example of that. As far as vectors themselves, they're going to come up in future problems. I just want to give you that heads up about that. Okay? Okay, so I just want to let you know that information. Let's get back to our derivative equal to 0. I should probably write it back. I thought I needed this space, so I started erasing everything to give me space on my board. Okay. So we set this equal to 0 to solve. And it's just basically our numerator is equal to 0. Okay. And now if you want, you can factor out the 2 to kind of give us a way to look at what t can be. Well, there is no t here. 2 cannot equal 0, but we can take a look at this set equal to 0. And if you look at that, you may be thinking, well, with the plus 1 here, it's a parabola that's entirely above what would be the t-axis. So there's no solution here. So what that means is that we have no critical number, okay, in order to determine whether the interval before was positive, meaning we got a curve that's concave up, or the interval after is negative, we have an interval where our curve is concave down. But don't worry, okay? So if you remember doing FDT or STT, we also want to take a look back at our original function, or in this case, dy over dx, and see where it's not defined. And it would not be defined when the denominator is equal to 0. So if we solve for t here, t would be 1/2. So this is our critical number that we're going to use to determine whether our curve is going to be concave down. So here we go. All right, so the intervals of t. So when we get to more of the word problems, t will probably not be negative. However, for right now, we're going to choose values, any values of t. Okay, you can choose any values of t, and you can choose negative numbers, you can choose 1/2, okay, you can choose numbers greater than 1/2 for t, anything that you want. You can plug it into both equations to find out what your x-coordinate is and your y-coordinate, and you can start plotting to create a curve. So that curve could be concave up or concave down, okay, based on your parametric equations. Okay, so it gives us some sort of curve. It turns out it is a function. All right, so we need to see what the sine of d squared y over dx squared would be. So this was d squared y over dx squared. I'm trying to like double, triple box it over here. So if we decide to plug in 0 into our numerator and our denominator, okay, we end up with a positive answer. Now, if let's say we plug in 1, that's a good number for the next interval, okay, we end up with a positive number over a negative number. Okay, and when we divide, it's going to give us a negative answer. So what does that mean? Is that we now have found, okay, that on 1 to infinity, okay, for values of t, or for the graph of the parametric equations, it is concave down. I'm abbreviating, of course, CCD, concave down. So that's the interval that the graph is going to be concave down. And these are the values for t. Okay, and that's how we leave it. It's okay if it's for the values of t. We are working with parametric equations. So I wanted to show you how that second derivative can come into play with concavity, because it might show up on the AP exam. And as you can see, it's just basically like the same stuff we were working with before. So do go back if you're a little unsure of, even quotient rule or, SDT or something like that. Review notes so that way you're a little bit more confident in these kinds of questions. All right, so hope everything's okay. Let me know if you have any questions. Good luck.